In this video, I'm showing you several example topologies so that you see how the basic topologies can be used or combined. The first scenario is a general picture of a university network which can be found in adopted versions quite a lot. On the top, you see two routers which are used for wide area network access. Inside of the network, there is basically a tree topology consisting out of switches. Two switches are on the top and more switches can be found in the two lower layers. However, the main difficulty of a tree topology is that if a switch fails, a complete branch cannot be reached anymore. To avoid this problem, there is additional redundancy in the network. There are redundant switches and redundant links, so that each switch may fail without affecting the network. Central servers and also the firewall are directly connected to the switches on the top of the hierarchy, while usual end systems are attached to the switches on the lowest hierarchy level. This topology is based on the principle switch where you can, route where you must. In some other networks, it may however be necessary to use more routers. This slide shows the physical topology of the German research network, which is called XWIN in its current generation. As you can see, fiber pairs are in use to interconnect the major cities in Germany, where you find large universities and research institutions. The topology can be described as several rings with some additional redundancy. The choice of rings is useful because it is quite expensive to rent such fiber. Therefore, you want to connect many cities with acceptable costs and be able to provide some redundancy in case of failures. Such a network is often at risk by construction work. Operators may damage fiber unintentionally with their diggers. In such a case, the repair time is usually several hours. On this slide, you have another view on the XWIN, but on the network layer. This level is also called the IP platform. The figure does not show a geographical view, but a logical view. There are the same locations as in the physical topology, but it's not only possible to connect direct neighbors. The important links with a capacity of 100 gigabits per second bypass some cities because the traffic is not relevant for the cities in between. The optical technology allows for such an implementation. If you take a look now at the topologies which we find here, you can also see interconnected rings. The general principle has been that these rings start at one of the major locations, Frankfurt, Hanover, Berlin or Erlangen, traverse other locations and then end at another major location. The interconnections between the major locations then close the ring. This picture on the slide is taken from a blog post where Facebook presented its own data center in Altoona in the US state of Indiana. So this is a view how the network inside the data center looks like. As you can see, there are a lot of interconnections using spine planes. The conclusion is that such a mesh network seems to be needed because the data which needs to be combined to answer requests is quite distributed.